Are you ready for the big finish? Test 2 practice, fall 23. Draw Lewis structures for the following. What does VE stand for? Valence electrons. How many for nitrogen? Roman numeral 5. I have my finger on the screen. Each fluorine is how many? Your Lewis structure better have 26 electrons in it. That's what that says. Oh, power might be going out again. Save. No, I hit a button over here. We had a power outage this morning and it ruined a lot of things for a lot of teachers. But I just hit the lamp button here and I thought something happened. Because we are very diligent. We will never give up. Are we on video already? Can I tell you the time when we had a power outage? And it was in Origo lab. I took our power backup and I hooked it up to the screen on top of a cart. And we did a lecture until we were kicked out by security in the dark. Okay, sorry. Yeah, we never give up. There's an evening class, early evening. Anyway, guys, moving on. What atom is going in the middle? N. And big N. Green, but it's big. We can see it. What are you going to surround it by? Try to be symmetrical. F. Are you going to go like this? Please don't. I'm going to do something. Students love trying it. Don't do this. It's just flat out wrong. Fluorine doesn't do that. It makes one bond. Don't. No. 3 F's symmetrically around the N, right? How about a triangle if you're looking for symmetry? Very nice. How many electrons have you used in constructing your skeleton? You need 20 more. And I'll put them in red. Why did I choose to do that for 6 of them? Why did I go to 6? Why didn't I stop like there? I want a full, what's the magic word? I want a full octet. So now fluorine has 8 electrons around it. Move on to the next one. You're up to 12, right? Out of your 20. And then 2, 4, 6, that is 18, I believe, right? I'm missing a lone pair, yes. Don't put a double bond. You will now have an octet violation on fluorine. Do not do about double bonds until after you've got all the electrons on the picture. Do not even talk about double bonds until you have all of the electrons on your picture, all 20. You can't do anything else except give nitrogen a lone pair because there's no other room. There's no more room is what I should have said. There you go. Now, you were very lucky in this one because now all the octets are full. You're done. If the octets weren't full, I would take a lone pair off of fluorine and now move it in for a double bond. But the octet was full. I'm not going to violate nitrogen's octet by doing that. That one is done. Congratulations. All right. So we're supposed to estimate the net dipole. Yeah. The dipole? The dipole, she asked a good question. I said I might do it as extra credit on the test. The dipole, what I'm going to do is, like on this one, I will make it an extra credit because it's not an obvious one. But on the next one, where I think it's a little clearer, I'm going to use discretion based on level of difficulty. Because this one, the triangle you drew, you just messed it up by putting that lone pair. Because that pushes the fluorines down. Do you remember that? When you put a lone pair on the central atom, it pushes all the other bonds away. So a quick redraw is in order. And I'm not going to make you use wedges and dashes ever. But there's your redraw. And that's where I consider a bonus because you got to remember to do the redraw. Well, now I'm going to because it'll mean something. Why do they point towards the F, all the dipole moments? The higher electronegativity pulls electrons more strongly. They should all be the same length. That last one looks a little long, doesn't it? They're all the same length? What's delta En there? The only reason you need this is when you read my question about scale. 4 minus 3 equals 1. So those arrows, we had a name for arrows that have a certain magnitude, like big arrow versus little arrow. They start with a V, vector. Yeah, those are vectors, and they're 1 unit long. When you draw in the next example a vector that's like 0.5 units long, like the difference was 0.5, it better be half as long as those. That's what I mean by scale. Okay? Well, yeah, good. She surmised logically that since all my red arrows are now down, there's nothing pointing up. There's no way their up is getting canceled. Your net is down. And therefore it's polar. Net equals down. Therefore polar. But I don't even think I asked, is it polar or not? Did I? Did I? I'm not even going to put that then. Oh, I'm not going to ask you, is it polar or not polar? I didn't on the practice test. Yes. The difference between the electronegativities is 4 for fluorine and 3 for nitrogen. I asked you how I knew those numbers. Front of periodic table. Okay. All right. Oh, your second molecule, you ready? Will be a little organic molecule. And the good news about that, you want to hear the good news? I'll wait and hear some silence. Not hearing it yet. All right, so your second example will be a small organic molecule. Okay, and the good news about organic molecules is I've laid the skeleton out for you. But nobody's going to try to pretend the H is between an oxygen and a carbon. Nobody's going to draw it in the middle and draw 2 bonds to H, are they? No. H must be bonded to the C because that's what's previous, okay? And these 3 H's are bonded to this C because that's what's previous. So let's do VE first. What's VE stand for? Valence electrons. How much for an oxygen? Oops, I thought I had blue. 6 for oxygen, 4. I'm just going across. 4 more plus 3 times 1. And yeah, we got 10, like you said, 10, 15, 18. You're not done until you have 18 electrons. Skeleton has O bonded to what? Don't say O bonded to H. O bonded to C. And C is bonded to, okay, C is bonded to C. And then H, separate. And that last C has how many bonds to H? 3. So 3 separate H's, right? So skeleton's looking like that. Don't I like this? Okay. All right. How many electrons have you accounted for with 1, 2, 3, 4, 5, 6 bonds? You have to come up with 6 more. There's my system to at least get all the electrons on the page. There's the 6 extra. See them? Now, carbon doesn't have a full octet, but the oxygen next door does. So carbon says, hey, help me. And oxygen says, well, I really don't have to own those 2 electrons. I don't have to own them. I can share them. It's not a big deal. In fact, the electrons get happier, but let's not talk about electron happiness. There, I put them back. That also is a pair of electrons, right? Bonds are a pair of electrons. Lone pairs are a pair of electrons. And we have a question. Control Z. He suggested this. So he suggested, well, I got an easy answer taking you quite literally. You said put a lone pair on the carbon. Now you have 20 electrons on your structure. It's wrong. You added 2 more electrons than you were allowed to. It's wrong. So you got to take off an existing lone pair and put it back on as a bond. That's the secret. Put that lone pair back on as a bond, and now you're officially done. And then there's a lot of bonds here, but I'm going to point out only one of them is polar covalent. Read my question carefully, and yours will also be polar covalent. I won't change those words. Is a carbon bonded to hydrogen polar covalent or pure covalent? Pure covalent because it's 2.5 minus 2.1. I don't want vectors for those. To me, they're too tiny to bother putting them on there. But when the difference is between 0.5 and 1.9, that's the definition of what type of bond, polar covalent, I need a vector for it. And what's the actual difference here? Is it 1.0 like our previous example? That is really nice. You know why? What do I have to do to the dipole vector, which I copy pasted from above? Because the difference was exactly 1 there as well. It needs to point along the bond towards the more electronegative atom. Which atom is that? C or O? Okay, rotating. Law of technology, huh? Pure covalent means non-polar covalent. Yes. So the net is the same. Net equals, there's only one polar covalent bond. I copied it. And I copied it too large. Is it this? No, it's still too large. That's the same distance. Good. All right, can't do that on the test. And we barely got done in time. That's good. All right, and stopping.